So for number 47, we want to find out whether the sequence here, it converges. And a sequence converges if it tends to a defined limit as n approaches infinity. So what we're going to do here is we're going to take this limit as n approaches infinity of our sequence 1 plus 2 divided by n to the power of n. So now the problem here is this n that is in the exponent, right? Because we're taking this whole thing and then we're raising it to infinity. And so this, we can't do anything with it right now. We're going to have to transform this. And what we're going to do here is we're going to take the function, we're going to take the limit as x approaches infinity of, let me clean this up, x approaches infinity of 1 plus 2 divided by x to the power of x. And the reason that we're doing this is because the function and the sequence, they go to the same place. They behave in the exact same manner. The only difference is that the function is defined for all real values, whereas the sequence is only defined for the natural numbers, right? But they definitely tend to the same place. So for example, if I have a random function that does like this, the sequence is going to do the same thing, except it's only going to be defined in the natural numbers. So n is equal to 1, 2, 3, 4, 5, and so on. But we can see that they head to the same place. So if I find this limit using the function, then it is the same limit using of the sequence. So we're going to do this. And so we have here that y is equal to 1 plus 2 divided by x to the power of x, and the problem here is this x that's in the this x that is in the exponent, right? We don't like that because we're going to raise to infinity. So what we're going to do here is take the ln of both sides. So we have that ln y is equal to ln of 1 plus 2 divided by x to the power of x divided by x to the power of x. And the reason that we did this is because if we take the ln of both sides, we can use the log laws and bring this exponent down in front, which is what we want, right? If we bring this exponent down, then we have dealt with our problem, which is raising to the power of infinity, which means that ln of y is equal to x times ln of 1 plus 2 over x. And now I'm just going to take the limit of both sides, right? So the limit of ln y as x approaches infinity is equal to the limit as x approaches infinity of x ln 1 plus 2 over x. Okay, and so if we take this limit as x approaches infinity, what we're going to have here, I'm just going to separately, if we take the limit as x approaches infinity of ln 1 plus 2 over x, this 2 over x, it's going to be 2 divided by infinity, right? So whenever you go 2 and you divide it by a very large number, that's going to tend to 0. So this is going to be ln of 1 plus 2 divided by infinity, that's 0. So that's ln of 1, which is 0, and so that's 0. And so this limit here, this is going to be ln of x, the limit as x approaches infinity of x. So that's just going to be infinity times this limit here, which we've just seen is 0. And so this is indeterminate form because we don't know whether infinity is winning or 0 is winning. Infinity times 0, we don't know what that is. So we do have a tool to deal with indeterminate forms, which is L'Hopital, but this is not in L'Hopital form because L'Hopital form is either infinity over infinity or 0 over 0. So we do have to transform this. And the way that we transform is we're going to just turn this around. We're just going to say, okay, this is the limit as x approaches infinity of ln 1 plus 2 over x divided by 1 over x. And I haven't changed the meaning of it, right? Because dividing by 1 over x, that's the same thing as multiplying by x. But now if we take this limit, this is going to be the limit of this guy on top, as we've shown before, is going to be 0, right? ln of 1 plus that goes to 0, so ln of 1 is 0, over 1 divided by infinity, well, that's just going to be 0, and hey, this is L'Hopital form, that works. So now we can use L'Hopital, so we can move to the side and say, and say here that using L'Hopital, we have to take the derivative of the guy on top and the guy on the bottom, right? So the derivative of the guy on top is going to be 1 divided by 1 plus 2 over x. That's the derivative of ln x, 1 divided by the argument, times the derivative of the argument, right? So the derivative of 1 is 0. The derivative of the argument is going to be 2 times, that is negative 1 over x squared, and then over the derivative of the bottom. So the derivative of the bottom is just going to be, let's see, that is negative 1 over x squared. Okay, and then we're taking the limit as x approaches infinity. Well, if we take this limit here, this is going to be equal to, we're going to be able to cancel these two, right? So this is the limit as x approaches infinity of 2 over 1 plus 2 over x. And so if we take this limit, this guy on the bottom, the limit of 2 is just 2, the limit of 1 is just 1, plus 2 divided by infinity, that is 0, right? So this limit here is going to be equal to 2. And now we can't forget that the whole thing here was, we found that this limit was equal to 2, so let's scroll back. So remember that we have here that the limit of ln of y as x approaches infinity is equal to 2, right? This here is our whole thing. However, we don't want ln of y. We want the limit of y. Remember, because y is this guy here, which is what we want. So what we're going to have to do is, to get rid of this ln, we're going to have to take both sides base e, right? So we're going to go the limit as x approaches infinity of e ln y is equal to e to the power of 2. And so we have here that the limit as x approaches infinity, this e to the ln, it cancels out, so we have the limit of y is equal to e to the power of 2. And that over here is our answer. Because remember that y was 1 plus 2 divided by x to the power of x. So this limit here is going to be e to the power of 2. And therefore, we can say this limit here by comparing with the function equals e to the power of 2. Right, so this is our answer here. And so we can say that it tends to e to the power of 2 as n tends to infinity. So because the limit exists, so an converges. And that here is our answer. So just to recap real quick, all we did was we represented the sequence with a function, and then we took the ln of both sides, we turned it into L'Hopital form, took the derivative, found that the limit here was equal to, the limit was equal to 2, and then we went back, because we had, in terms of the ln, we had to take base e of both sides to get rid of that ln, and then we found that the limit was e to the power of 2.